So today I'm going to start a new topic, which is World Wide Web. There is some leftover material from last time which was on Paxos. I'm going to defer that to a later class because I do want to mention some of this because it's relevant to the lab that is out. So I don't want to wait until next week to cover that material. Okay, so I'll come back to Paxos. The other announcement I want to make is if you look at the schedule, there is a makeup class this Friday, but I'm not going to have it. Okay, I think it's just not been it's an inconvenience basically to many of you, and I just think that we did too. Let's stick to that. I'm going to restructure the topics a little bit, compress a few things, and then we can still cover everything we wanted without having to have another lecture. So I will go ahead and cancel the Friday lecture that's on the schedule, okay, and make some adjustment to the rest of the topics. Okay, so let's get started. So I'll talk about the World Wide Web. I did want to spend 1 minute talking about the Raft consensus protocol because that's part of an extra credit option in the lab. It's strictly extra credit, so please don't try to attempt it before you finish the lab itself. Okay, so make sure your lab is in good shape before you try to do anything more than that. But should you want to think about Raft, first you got to read the paper. Okay, this is not going to give you all the details. So there is a paper on Raft. It's linked off the reading list, I believe. Go read it. Okay, try to understand what Raft consensus is. But by and large, it was proposed as a way to provide consensus, but in a more understandable fashion, because Paxos, as you will see, is very hard to understand and reason about. So what Raft does is it implements something called state machine replication, or SMR. Okay? The very basic idea of what SMR is, if you have a set of replicas that are receiving requests, you essentially want to order the requests and process the requests in exactly the same order. Okay? Now in your lab 3, you have 2 replicas of the order and a catalog server. Okay, they are going to get concurrent requests from clients. Okay, there is no specific requirements in the normal part of the lab that you actually have to process them in exactly the same order. But you will realize that for correctness reason, that has to actually happen. Otherwise, what might happen is if you have the last item, there's only one item for a book, let's say, and then you receive 2 concurrent requests. If you process them in different orders, in one replica, user 1 will fail, in another replica, user 2's request will fail. You don't want that to happen, so you want to process them in the same order. Okay, Raft is actually going to give you a state machine replication, which essentially is implemented as a replicated disk log. Okay. So essentially what you do is you take all the requests and you would write them in the log, and you got to agree on the ordering. That's the consensus you are trying to achieve in case of state machine replication. And then so you are going to execute the request in log order, and if the log is the same across all the machines, you are going to execute all the requests in exactly the same order. Okay. So that will ensure correctness. You will not have transactions or requests getting processed out of order at different replicas and causing problems. So essentially you have to read the paper to get the details, but you will have to first do leader election, elect a leader. The leader will then actually send log entries to all the followers, and then you got to use the Raft protocol to decide on the ordering. And then when you commit, you say this is what we all agree to, saying the next request is request I. You write it to the log, and then basically you keep appending, and the logs at all the replicas are exactly the same, which means that the requests are processed in exactly the same order, even though they may have been received out of order. You basically then agree on the order and process them in the right order. So that's basically what Raft would do. So if you do attempt the extra credit portion, you will have to implement this, and that will guarantee that every replica you actually implemented is processing all your requests in the same order. Okay, so that's a very high level description of what the extra credit part is and what Raft is. We will come back to consensus, and then we'll talk about what Paxos does to do this, and then you will see the difference between Paxos and Raft. Yes, please. Question.
Without using the Raft consensus protocol, so for the non-optional part of the homework,
yes.
What's the recommended way to make sure that all the replicas have the same stuff in the database?
Okay, so the question is how do you ensure the database is consistent, right? And you are asking the failure case or not, just the normal case, the non-failure case, right? So ideally you would want to, I mean, even when the non-replicated case, you had issues of transactional semantics. Concurrent requests were coming in, you didn't want to have the requests override one another and so on. You could have implemented some simple locks and things of that sort, right? So that's one approach. There are many ways to implement replication, right? So you can have the front-end node send the same request to all the replicas, that is multiple writes or replicated writes, or you can do master slave where you elect one of the replicas to be the master. It receives all the requests and then it sends the requests in the same order to all the other replicas. That will ensure you don't need consensus in that case because all the requests are coming to one node, and whatever it does, it will send them in exactly that order, sequential order to all the other replicas.
What's the purpose of having load balancing if you have to send them to all the catalog servers or order servers anyway?
Right. So question is, what's the purpose of load balancing? So there are reads and writes. You will not send reads to all of them. In this case, if you actually do that, the writes have to go to every database by definition. Load balancing does not help you because you have to keep all the replicas consistent. Whether the front end sends it or you send it to a back end master and the master sends it, it doesn't matter. It has to go to all of them. So the load balancing is effectively only being used for reads in this case. Typically, the reads will presumably be more frequent than writes. Okay? Any other questions? Yes, please. Does the consensus introduce too much overhead? The consensus will, of course, introduce overhead. There is no question about it. But it is necessary for correctness reasons, unless you use master save type configurations. Right? So then you basically just say master will do the ordering and tell everyone this is what you do. Right? So that is still okay. But yeah, it will introduce additional overhead. There is no question.
Because while I was doing the lab, because when I use some sort of consensus protocol between the replicas, they delay that.
Yes. So I mean, you can easily expect that kind of overhead where, because you are doing LAN, so the delays are anyway small, but you will see increased delays. That's okay. You should just report it. We are not asking you to implement an efficient consensus. This whole point is to understand what consensus is used for. Now, the only thing I will mention is when you do things like master slave, if there are failures, things don't work. But in consensus protocol, so long as the majority agrees, things are still fine. So this works in the presence of failures, which is why it is actually a better approach. Yes. Yeah. So is there a difference in overhead? Well, you should read the paper and see if it is actually understandable. All consensus protocols are hard to understand, even though this claims to be more understandable than the rest. Having said that, I think Paxos is actually very more general than what Raft is trying to do. It applies in slightly more cases because there's something called multi-Paxos and single Paxos where you can have multiple leaders. Raft actually makes some simplifying assumptions and tries to do things differently. So that's one way to think about it. Okay, so let's continue. The goal today was actually to talk about the web. So we'll go through very quickly some high-level details of web servers and web clients and so on, but spend most of our time talking about consistency, web caching, how to ensure consistency. Because if you remember when we talked about the fault tolerance, consistency, replication, I did say we'll come back to this when we talk about the web, try to understand how this is actually addressed. Okay. So this is the picture you want to keep in mind. Okay, as a web client as the browser, it's sending HTTP requests to the server and it's getting responses back. Okay, so these are request response type scenarios. We have seen this kind of picture when we talked about, I think, lecture 2 or lecture 3. I don't even remember now. So this is typically the architectural view of what a browser does. We'll see it has many different components. There is an XML parser. There may be client side interpreter if it does things like JavaScript. There's a rendering engine. There's a browser engine that's actually talking to to the servers. There's a UI that actually renders things and so on. And when we are talking about all of this in the context of threads, we said you can have multiple threads or processes. Each of them can do their own little bit and then implement browser functionality. So we won't go into this again. What I do want to sort of start focusing on is this notion of a web proxy that's going to sit between the client and the server. Okay, here the proxy is an intermediary for the server. If the client requests are going to the proxy can satisfy or service the request locally, you're done. If not, it's going to forward the request to the server and send it back. Okay. Now, just to illustrate that the proxy can actually do interesting things, we made the server an FTP server, not an HTTP server. And you will see that the browser is sending HTTP requests. They get translated into a FTP request in this case. So this is a very trivial example to show that proxy can also do protocol translation, not just do simple things like caching and things of that sort. In many cases, it might do things like transcoding, where it gets the content in one form and it basically renders it for some other device. For example, it may redo a web page for display on a mobile device. Or you might have a high definition video. It might make it a standard definition if you're seeing it on a small screen. So lots of interesting things can be done by proxies. For today's class, we are mostly going to look at the use of proxy for caching. Okay, we'll come back to that in just a moment. Okay. Here's a picture from the book of what the architecture of Apache Web Server looks like. Okay, so there are lots of boxes, but the more important thing is two things to keep in mind. It is using what is called a pipeline processing. Okay, so essentially requests come in, they go through a series of stages where there is some intermediate request processing, it hands it to the next stage and so on. Okay, and each of this is essentially very modular. Okay, if you've actually seen how to configure Apache Web Server, you will see that there are a set of modules. You can turn them on or off, and each module will do part of the request processing. Okay. So again, Apache uses one of two architectures. So it uses a multi-process architecture, where there's a dispatcher and set of not client, but rather slave processes, which will actually do the request processing. It also uses multi-threaded architecture, where you can use threads rather than processes. Okay, which one you use again is highly configurable, and then it will have static pool, not static, rather dynamic pool of processes or threads that can be varied based on load. So a lot of sophisticated features that you would use when you have concurrent servers. Okay. Now this picture we have seen before. This is essentially a multi-tier web server. Okay. You have implemented simple versions or variants of this in your lab. So you have in this case 3 tiers. So there's HTTP tier, just implementing simple HTTP logic. Okay, there is essentially the application tier. In this case, it's shown as CGI, but this could be anything. It could be Python, it could be PHP, it could be Ruby on Rails, whatever you use to write your application, and essentially sits in the middle tier. So that's your application logic. The backend tier is essentially the database tier. Okay, so that's where you will actually store all of the data and so on. And we've seen this kind of processing multiple times now. So requests come in, they're processed at each tier, sent to the next tier, processed again, sent to the next tier, and so on. You can have any number of these tiers depending on the complexity of your application. Okay, this is the old style way of writing applications. These days, you essentially use even smaller components, which are called microservices. So they might interact in interesting ways, and there may be a lot more components involved in request processing. Okay. Okay. So the last picture, again, we have seen this before, is one of a web cluster. Okay. So here you have a front-end node and a set of back-end servers. Although these servers are stored as individual components, each of them could be multi-tiered. Okay, this is a logical organization. Okay, so each of them could have multiple tiers and maybe replicated databases and so on. Okay, so for the purposes of just understanding the cluster, we have to understand each of them is replicated. Requests come in and they can get partitioned across the multiple replicas of the server. This way, the cluster as a whole can service a lot more requests than an individual machine. Okay. It's a very standard way of scaling up your capacity of the web server. Okay. You essentially will cluster it and replicate it across multiple machines. Not unlike what you are actually doing in the lab. Okay, you have a very simple version of this, but this is essentially how many of these web clusters are architected. And then given that picture, the way you might actually service requests, okay, will involve first the client sends the HTTP request to essentially what is called a load balancing switch, which is going to receive the request, and that's what is shown here. That's essentially your front end node. Okay. The front end node might itself have multiple components. Okay. So essentially it has a load balancer built in. Okay. In this case, that's actually shown as a dispatcher. So the load balancer decides for either every request or every user session which replica to use. Okay. Typically, load balancing is not done at a request granularity, it's done at a session granularity. Okay. Every user or browser, when it connects to the server, you start a new session. Okay. Once you get mapped to a replica, all your requests are sent to that replica. The reason this is done is the replica might contain state. Okay. If it's a e-commerce site, you might have something in the shopping cart, for example, that state of that session. If the next request goes to some other replica, that memory state is not replicated elsewhere. So you got to keep sending all the requests of a user session to the same replica. If you just do round robin load balancing on a per request basis, you are not going to get that property. Okay, you'd only do this if all your services are stateless, then it doesn't matter which replica services it. If you have stateful information, then you have to ensure that requests from a browser session go to the same replica. Okay. So the way the dispatcher will do this will either be on a request basis or a session basis. But once it has figured out which of the I guess there are two replicas here, which of the replica gets to service the request, then the switch will then start forwarding all the requests to that session. Okay, so that's basically, now the dispatcher and the switch, although they are shown as two logical components, they might sit on the same front end node. Okay. They don't have to, but typically they will be on the same front end node. Okay. So very quickly, the very basic information about HTML and HTTP before we go move on to web caching. So typically when you request an HTML page, it comes back to you, the response essentially comes back to you as a MIME document. Okay? And this is the same protocol that is essentially used in email when you send attachments. Okay? So your email, when you put in an attachment, it is self-describing. It says what is the format of the attachment, what is the content in the attachment, and so on. And the same thing is true when you get an HTML web document. You can essentially have type saying this is a text document and it has it's HTML text document, or it's an image, it's a JPEG image. It's audio with certain encoding or video and so on and so forth. Okay, so this allows the browser to know how to interpret whatever object has come back. Okay, is it a web page with simple text? Is it an image? It's a video document. The browser has to know. Okay, so the response will typically have the encoding and information about what the content is when it comes back to you. Okay, so this is essentially called MIME encoding, the same thing that you have in emails. Okay, so now although you are essentially getting HTML documents from the server, the protocol you are going to use for communication is HTTP. Okay, so you need to have a little bit of understanding of how HTTP works. So here is a client, here is a server. Okay, essentially whenever you click on a link or you type some address in your web browser, your browser is going to set up an HTTP connection with the server. Okay. Now maybe you retrieve one page and you click on another link in that page. If that link essentially refers to the same server, you will make another HTTP request. Okay. And you will see that in this case, this simple example, there are 3 connections that have been made to the server to retrieve 3 different items from the server, maybe an HTML page or a second HTML page and so on. So every HTTP request is going to set up an HTTP connection with the server. Okay, and if you are now retrieving a document which has lots of images, all of them are on the server, each of them will require another HTTP request to be made and so on. Okay. So if you use what is called the HTTP 1.0, which was the original protocol, each connection requires a separate TCP connection, and it will have to, you will have to set up a socket connection and so on. So it is going to incur overheads, okay, from the OS perspective. So what HTTP 1.1 did was it introduced this notion of a persistent connection. A persistent connection says once you set up a connection with the server, keep it alive, okay, keep that TCP connection alive, so that if there are additional requests being made, you use the same connection. You don't have to start a new TCP connection. Okay. So you see now the same example as before. Essentially, all the requests are going on a single socket connection. Okay. They are essentially reusing that connection for multiple object retrievals from the server. This is going to strictly reduce the overhead on the server, because you have, if you have lots of clients setting up connections to the server, there will be lots of socket connections open here. Eventually, you are going to reach some limit, because you can't have infinite socket connections. There's still an OS limit. So you don't want to hit that limit to the extent possible, otherwise you turn away requests. Okay, so trying to limit the number of socket connections is actually an important thing. But that also raises many other questions. Okay, so how long should the client keep that connection open with the server? Okay, so suppose you have retrieved a web page from a server, okay, and to do that the browser set up a connection to the server. Okay, so how long should it be open? Because you might read that text and then maybe 1 minute later click on another link that triggers a new HTTP request to that server. Okay. If you had shut down that connection, then you would have to start a new one. But if you had kept it open, then you can reuse the old one. Okay. But then that begs the question of how long would you keep it? Would you keep it for minutes, hours? Okay. The longer you keep it, the more, and if it's idle, you are just wasting resources. Okay. So there are some trade-offs you have to think about, which say, although the connection is persistent, which means it is kept alive, okay, you got to decide what is the lifetime of that connection. What kind of idle timeout would you have, saying maybe there's no activity for n minutes. So now I'm going to shut it down with the assumption that the user is no longer going to send any new requests. So you can tune that parameter, which will also decide how much resources get consumed and so on. Is that clear? Okay. All right. So HTTP, which I think you probably know from writing REST interfaces, essentially has 4 operations it supports. Okay. So get allows you to get a document or an object from the client. Put allows you to store a document. Okay. Post allows you to essentially add data to a document. Post is what you use to submit web forms and so on. And delete allows you to delete a document. Typically, browsers don't have delete access. You can't go and say delete this web page from the server, but it is a supported operation under HTTP. Okay. So all HTTP requests are essentially going to have one of these 4 types. Okay. So the most common one is of course the get, where you're just simply fetching web pages or images and so on. Okay. When you post any form, you essentially have to do or submit any form, you essentially have to send it as a post request. Okay. But you can also use put to store documents if you want to upload a document and things of that sort. Yes, if you're uploading something to a website using a browser, typically it's going to use a put to upload that document. You upload an image to some cloud service and so on. Okay. So all of these HTTP protocol essentially is one of 4 types of requests. So it's fairly simple protocol as protocols go. Okay. So with that in mind, I'm going to spend a little bit of time talking about REST and so on, which is something you already all know. But we'll start with the basic concept of a web service. Okay, so you have to distinguish between interactions between a browser and a web server, and between 2 components that are simply using HTTP to interact. Okay. When you have a browser, you essentially have a human that's trying to actually access contents and so on. Okay. But the same concept can be extended where 2 components of a distributed application are simply used communicating over HTTP. Okay, they're simply exchanging information over HTTP. So in this case, the first component or the server is exporting an HTTP interface that the second component can access and perform operations on the server. Okay. So that is what is called a web service. Okay. So essentially, you are exposing an interface that is HTTP based that a client can use. And in this case, the client is not necessarily a browser. It could be any other client which is implementing a larger application. okay, essentially a program that is going to do this. Okay, now in the old days of web services, you had heavy duty protocols such as SOAP that were essentially used to do this. Essentially, it was a way to do RPCs using HTTP. Okay, that's what a web service is. It's essentially using HTTP as the protocol, and each request is essentially an RPC request that you are sending over to the server. So there was a protocol that was defined which was called SOAP. You could write an object service description using something called web service description language. There's a compiler that would generate a stub. Okay, you'll see that there are stubs here. Okay, and then you use that stub to essentially make SOAP requests which were going over HTTP. Okay. So essentially, they implemented a full-fledged RPC system using HTTP as the transport rather than using TCP or UDP as a transport. Okay. Now, this ended up being far too heavyweight. So you will see that SOAP is actually not used, but you have REST interfaces that are used, and we'll try to understand the distinction between writing a web service using SOAP and using REST to do this. Okay. So SOAP is an acronym that stands, that is basically Simple Object Access Protocol, and essentially it uses XML as a way to exchange information. Okay. If you make a RPC request, you are going to send it as an XML document, and all the method you call, all the parameters are essentially sent as an XML document. And then if you want to get a response, you also will get it as an XML response. Okay, so here you will see that this is essentially an XML document, but essentially the method you are calling is an alert method. And then you essentially have an argument, which is a string that you are going to pass to that alert method. Presumably, that's going to trigger an alert that's actually sent to the user. Okay? But you will see that there are lots of XML body and things of that sort, which means you want to call that simple method, you have to send essentially a fairly large piece of text between the application component 1 and application component 2. Okay? And because SOAP tends to be very heavyweight, it never became a success. It was way too much overhead to make simple calls. So then some web designers said, how do we take this idea, which is a good one, where you're using HTTP as a way to write distributed applications and using HTTP interfaces, but how do you simplify it? Okay, so that essentially gave rise to this notion of restful interfaces. Okay. So whereas SOAP was designed for arbitrary distributed application where you could have n interacting components. Okay, they could all interact using XML and XML RPCs and things of that sort. REST was designed in a much simpler manner. It was said just point to point. Okay, there are only two interacting components. Okay, so each one is going to expose an interface, another component will essentially access it. Okay, and it uses HTTP. Okay, so SOAP doesn't actually have to use HTTP, it can do other things, but REST is essentially just using HTTP. You will use GET to do reads, you can use POST to do create, update, delete, PUT to also do create, update, and delete to delete something from a server. So you essentially use the same 4 methods that HTTP used to essentially implement RPCs or in RPC-like interfaces. So here's an example of a simple REST request and a response. So in this case, you are going to send a GET request, and this is your REST interface. It says get stock price, and then you have the name of the company. Okay, so you're essentially making a call to retrieve or query for the stock price of a company. Okay, and then it essentially have a host that says that's the machine you want to send it to. Okay, and here's the response that has come back. So saying that's the HTTP header, and essentially here is the response. Just come back to you as an XML document. It doesn't have to. You can get it in JSON or any other format that is suitable for the client to parse. Okay, here it has come as an XML document which says here is essentially the company name, and that's the stock price of the company name. Okay. This could have come back, as I said, as a JSON object as well. Yes?
Is that triple N a placeholder also?
No, the triple N is just a placeholder for the length, actual number of bytes in there. Okay. So this is REST. Just to give you an example of how this same thing would translate using SOAP, you will see that's the same example. If you are using SOAP, this is what you would send. Okay, so you would essentially have an XML document with the whole set of URL, and then you essentially say, I need the stock price of IBM, but everything has to be self-describing. That's how XML works. So your content request is much bigger. The response is also much bigger. Everything has to be self-describing and so on. So it comes back as an XML response. Okay? So the overhead of doing this is much higher using SOAP because the messages are longer. The processing of the messages take longer because you have to XML parsers and so on. Whereas here you are sending a simple HTTP request and getting a simple response. In this case, the response is indeed XML, but it's much shorter than what you had seen earlier. So with that very simple example, it's instructive to compare SOAP, which was the original way that designers envisioned you would write web services, and RESTful interfaces, which is essentially how people actually write web services. Okay? So this was never actually commercially a success. This is what most of the people actually ended up doing. So what are the differences? Okay, so both are language and platform agnostic. Okay? You can write RESTful components using any language of your choice so long as the interface is HTTP. Same is true of SOAP. Okay, so language and platform are agnostic. SOAP is also transport agnostic, which means it will run on HTTP, but it is not required that it runs on HTTP. It could run on other protocols if you want to. Okay. RESTful interfaces are strictly HTTP based. You have to use HTTP for your components to interact. Okay. SOAP was designed for general purpose distributed computing. Okay. RESTful web services typically are essentially point to point. Okay. Two interacting components. You will never have n interacting components to do one operation. You can have n components, but their interactions always pairwise. Okay, so point to point. So you will essentially have I talking to J, okay, without any. So there are no intermediaries and so on. Okay, this is fully standards based. Okay, you will see a set of standards were designed. There was essentially a definition language, how to write this and so on. Okay, RESTful web services have no standards. So long as you adhere to the interface, your application is still considered RESTful. Okay? So essentially, this gives you more flexibility as well in how you write your application and so on. Okay? So this is meant to be extensible, it is heavyweight and so on. Here, the learning curve is not that much. Okay? So now if you understand HTTP, you understand the basic notion of how interfaces work, how RPCs work, you can actually write applications. Essentially, they communicate over HTTP. Okay? And as you can imagine, you did this for your lab. Presumably, many of you didn't ever have prior experience doing RESTful interfaces. That wouldn't have been the case if you had to write a SOAP application. There would be a much bigger learning curve, given that there are lots of tools to learn and so on and so forth. Okay? And as I said, this is essentially tied to HTTP. Okay, you cannot use other protocols. Okay, I should mention that RESTful stands for representative state transfer, because essentially it's using HTTP as a way to make RPC-like requests, but also pass information back and forth. Okay, so that's an acronym for RESTful. Any questions on this before we move on to web caching? Okay. So in the remaining 45 or so minutes, we'll actually get to the main topic. So there's a very quick, broad brush introduction to web and web standards and so on. But the main goal of the course class, rather, not the course, was to actually look at web proxy caching. Okay. So we'll look at many variants of web caching. Okay. The standard one is there's one proxy sitting between the client and the server. The proxy is going to implement a cache. Okay, when the web browser makes a request, you check the cache. If you have a cache hit, you respond. Otherwise, you go to the server. Okay, now there is a variant of this which is called cooperative caching. Okay. In cooperative caching, you essentially have a set of proxy caches that are going to collaborate on a request. Okay. You send your request to one proxy. If that proxy has the object you're requesting, you are done. You get back a response. If not, it's going to ask other proxies saying, do you have this object? Okay. So and if any one of them have it, they're going to respond to you. If none of them have it, then you are going to go back to the server and try to fetch the object. Okay. So this is called cooperative caching. Okay. This general concept is not specific to just web caching, but there are other contexts where you have caches cooperating. The reason you do this is essentially now your cache essentially looks like the union of all the caches. Okay. So, if any of the local caches have it, then you can get a cache hit. Otherwise, if you are only limited to the one cache that you are looking in, and if there is a miss, then you go to the server. And presumably cache misses are expensive. So, as far as possible, you want to get hits rather than misses for your cache. Okay. So, there are some interesting implications of how we can actually integrate this notion of cooperation into caching and so on, and we will look at several ideas and protocols to do this. Okay. So, here's the picture with one proxy cache, which we will start with, then we will look at cooperative caching and so on. So, typically you will send HTTP request directly to the server. Here all your requests are going to go to the cache, okay, and then the cache will, if there is a miss, get your object on the server. So, now with this picture, let us think about cache consistency and so on, then we will get to cooperative caching. Okay. So, if you have a proxy sitting between the server and the client, over time it is going to fetch web pages from the server and keep it in its cache. Okay. Now, if the page has actually been updated on the server, your cached content is going to be stale. Okay. If a new request comes, you do not want to use that stale data to service that request. Otherwise, the user or the browser gets an old version of the web page, not the latest version. So, that is going to result in the question of how are you going to ensure consistency. Okay. We are going to look at consistency along two dimensions. Okay. We will look at invalidations or updates, which is what information you send to the cache to keep the content up to date, and push versus pull, which says whose responsibility is it to keep the content up to date. Okay. So, these are two independent dimensions, and based on how you actually combine them, you will get different variants. Okay. But we will start with push and pull, and then we will talk about invalidate and updates within the context of each. Okay. Let us start with a simple push based approach. Okay. So, here is a tiny picture that shows what is happening. So, in this case, the web server is going to track every proxy that has requested content from it, and it is going to track which web pages that it maintains are stored at which proxies. Okay, so, it has essentially kept this information. So, now if a web page changes, okay, because maybe the user or somebody updated the content, it already knows which proxies have cached that specific web page. Okay. In that case, you can essentially push either an update or an invalidate to the proxy, saying this web page has changed. Okay. Invalidate simply tells the proxy saying the web page has changed, discard the version you have in the cache. Okay. Update actually sends the new version of the page, saying, so that is an implicit notification as well as the new content has been sent out. Okay. So, essentially the idea is very simple. In a push based approach, you track all the proxies that cache requested any content. If any web page is modified, you are going to notify each proxy that has it. Okay. Notification type could be invalidate or update. Then the question is which one would you use and when. Okay. And that depends on many criteria. If a web page is popular, meaning that there are lots of requests from users, okay, you are better off sending an update, because if you send an invalidate, that proxy just discards the web page from its cache, it is likely that in the near future somebody will again request that page. That will result in a mess, which will cause you to come back to the server to fetch the new version of the page. Okay. If you had just sent the update, you would not have to do that, because you would say here is the new version of the page, just replace the version you have in the cache with this new version. Okay. So, then subsequent requests are not going to see a miss or a longer latency to retrieve the object. Okay. So, the basic strategy is you can use updates for more frequently accessed object or more popular web pages, and you can use invalidate for less frequently accessed or less popular web pages. Because if a web page is not popular, okay, it has not a whole lot of read requests, there is no reason to send a new version, because there is some chance it may never get accessed by any other user at that proxy. So, why waste extra bandwidth sending a new content? Okay, you just send a simple message saying just discard it from the cache. Okay, so, you can use popularity based metrics to decide between sending invalidates or updates, but you have to send one or the other, because this is a push based approach. Okay. Now, advantages of push based approach is you are going to get better consistency guarantees. Okay. As soon as the web page changes, you are going to notify all the proxies. Okay. That notification is not instantaneous, there is still network delay. That is why I said tight consistency, not strict consistency. Strict consistency essentially says that you will essentially have to send that notification in 0 time. Okay, so between the time it has changed and time it takes for your notification or update to hit the proxy, you might still serve stale content, but that's okay. It's as tight as you can make it because you are only limited by network delays. Okay. In this case, the servers are intelligent, proxies are passive. Server is doing all the work. It's a server push approach of consistency. Proxies are just essentially getting all these updates and notifications from the server. Okay. Now, the disadvantage is this is going to make your HTTP server stateful because it has to track which proxies have cached content from the web server. Okay. HTTP by definition is not a stateful protocol. Okay, there's no, if you read the spec of HTTP, there's no state in there. You basically get a request, it's a GET request, you just serve it and send back a response. That's it. You're not keeping any more state. Okay, in this case, you essentially made the server stateful. Okay, that's a disadvantage because if the server crashes, the state is typically kept in memory, and you restart the server, you have lost information of which proxies are caching content. Now, if a web page changes, you cannot notify the right proxies because you don't know anymore. Okay, so that's a problem with keeping state. That's a general problem with keeping state in memory. If it's basically not tolerant to server crashes. Yes, question.
In lab 3, we validate requests, and if they're not in the cache, then the invalidate is just ignored. Should we instead be keeping track of the data that's in the cache?
Right. So the question, if I may repeat, is in the lab, you are saying you send an invalidate to every replica regardless of whether they cache something or not. Okay. The smart way to do it is to actually track and only send it to the replicas that have it. Okay. What you are saying is a broadcast based approach that says send it to all replicas. For the lab, it may be okay, just so that you know, because only 2 replicas. In the web, that's not going to be okay. If there are 10,000 proxies, every time a web page changes, would you send 10,000 messages? Only 5 of them had the web page. That doesn't make sense because you got to be smarter than that. So if you made that design decision, you should document it and say, here are better approaches. You don't have to change it, but certainly there are better ways to do it, which would involve tracking and selectively sending the notifications. Yes, question. Okay, question is caching similar to edge server architecture? So proxies could be deployed, go back here, right? The server is at some distant server somewhere, in the web server. Okay, now proxies could be deployed anywhere between the web server and the end client in the network. The closer the proxy is to the browser, the lower the latency. The whole reason you put this is you want to service requests faster than going to the server. Okay. So closer you are, the better off you are. Okay. Edge server is simply a way, edge server simply means you put some computation at the edge of the network. Okay. One use case for edge server is to actually run a cache on the edge server. But edge servers are not the same as proxy server. Edge server simply says where is the server located. It doesn't tell you what does the server do. Okay. Proxies say that it's essentially doing proxying. In this case, the proxy cache. Okay, you could certainly deploy it on the edge, but you could deploy it elsewhere in the network as well. Anything else? Okay.
How should we handle stateful requests with the web cache?
Okay, repeat the question.
So for the web cache, like we can't have a stateful, we can't cache a stateful request. Like let's say we have the homework. If the client is sending a buy request, we cache the number of values that are still available. We might tell them something that's not actually.
Okay. So you are asking a question about specifically about buy requests. So one thing you want to keep in mind is this is not specific to web. Anytime you have caching, you got to distinguish between reads and writes. Okay. Reads, to the extent possible, you want to service from the cache as long as your cache is consistent. Okay. Writes, you got to be more careful. Okay. There are actually 2 types of ways to handle writes. There's something called write through caching and write back caching. Write back caching simply says that any writes or updates are essentially first written to the cache, they return, and then the cache is going to flush it to the actual server later. Okay. But then if the cache actually goes down, meaning it crashes, then you have not actually propagated that write to the actual server, but you told the client that your request actually succeeded, even though it got never returned to the server. So write back is always more efficient, but it is not very robust to failures. Write through essentially is whenever a write comes, send it off to the server, wait for it to be actually processed by the server. Okay? So the safer thing always to do is to do write through. Okay? All right. So coming back to this, the other way to do proxy caching is pool based. Okay? So everything is flipped in this case. Now the responsibility of cache consistency is on the proxy, not on the server. Okay? For every web page that the proxy caches, periodically it's going to poll the server saying, has this web page changed? Okay? If the answer is yes, then you essentially discard the web page from your cache. So you are essentially going to check with the server periodically to see if the object has changed. This can actually be done through an HTTP message, which is a special type of a message. It's a get message, but you can essentially specify a condition. It's called a conditional get. Okay, so it's called an if modified since get message or an IMS get message. So you say get this object if it has been modified since, and you specify a timestamp, saying if it changed since noon, then send me the page. Okay, so the answer may be no, it hasn't changed. So then you basically know that the web page has not changed. So you can do polling using actually standard HTTP using what are called IMS messages. So you can ask, since I got it last, has it changed, using conditional gets. Okay. Now there's also the question of how frequently should you poll? How often are you going to do this? Right. So should you do it every minute? If your 1 million web pages cached, are you going to send 1 million requests every minute asking all sorts of servers has the web page changed? That seems entirely wasteful. Okay. But should you then do it once a day? But what if the web page changes very frequently? Right. So there are all sorts of issues you got to think about when you decide what the polling frequency should be. Okay. Now there are many ways around this. One is when the server sends the page to you, it can actually specify an expiration time, or what is called a time to live value, saying most likely it will not change for the next so much time, and that's called the time to live. Okay. So you can use that as a hint to say, okay, maybe I'll wait for the TTL to expire, then I'll poll the server. So you might get a TTL of 20 minutes. So then you say, I'll cache it for 20 minutes, and if that expires, then I will poll. Okay. But the TTL is just a hint, it's not a guarantee. Because the web server cannot guarantee that a user will not change the web page. It's just giving you some estimate of how likely is it for the next update to that web page to occur. Okay. So in this case, the server is giving you some information that allows you to figure out how frequently to poll. Okay. But the proxies can also make this decision themselves. Okay. So you can dynamically figure out how frequently to poll for an object by discovering the update rate on that object. And the technique would works as follows. You essentially start by polling very frequently. Let's say you fetch a new web page into your cache. Okay. You poll it maybe 1 minute later, okay, using an IMS message. If the server says hasn't changed, then you essentially increase the poll duration. Next time you poll after 2 minutes. Okay, check. Again, if the web server says does not change, you keep increasing. You could increase additively or multiplicatively. How you increase doesn't matter, but you keep gradually increasing the poll duration. At some point in time, okay, you are going to get the web page might actually change, and the server will say, yes, it changed. Okay. So now you at least know the time between two successive updates, because you know when you started polling and when it was changed. So you can essentially then set that and poll at that rate. And if it changes again, you can reduce it, saying maybe I should be a little more conservative because I don't want to miss updates. Okay. So now if you are frequently changing objects, by essentially gradually increasing it until you discover the right update rate, or assuming the update rate is somewhat fixed, not fixed, but has some update rate that makes sense for that object, you can actually discover it by essentially polling at different rates. So essentially you are probing the server to figure out how frequently I should poll. Okay. Less frequently accessed page will automatically get long poll duration. So you might end up polling every 6 hours or every day, but very frequently changing pages Okay, you will not be allowed to increase the poll duration because every time you do it, you will see web page change. So, you will try to keep it short and keep polling frequently. Okay. So, this is an approach where you are essentially adaptively trying to figure out how frequently to poll. Okay, keep in mind there is no guarantee. This is not going to give you strong consistencies. All it is doing is reducing the consistency overhead. You do not have to poll too frequently. Okay, so, the less popular pages you poll less frequently, the more popular ones you poll more frequently. Okay. So, this is called intelligent polling, and you can essentially implement that into a proxy based approach and implement pull. Okay. So, again let us look at advantages and disadvantages. So, advantages, you can implement this using HTTP. There is no additional protocol needed, none of that. It just rides on standard HTTP. All you are doing is using conditional gets to figure out if a web page is changed, and you can use that information to determine polling frequency. Okay, server remains stateless. All the intelligence is at the proxy. This is a client pull approach. Server is not doing anything other than responding to proxy requests. Okay. It is resilient to both client and not client, server and proxy failures. There is no state, okay, other than the poll duration. There is no state. Okay. If this proxy crashes, you restart with the conservative small poll interval and keep increasing. So, there is no need to keep any state at all. Okay. So, much simpler to implement in that sense. The disadvantage is weaker consistency guarantee. Okay. There is no guarantee that between two poll durations or two poll requests that the web page has not changed. Okay. Until the next poll, you will keep serving stale content because you do not know. Server is not going to tell you in this case. It is your job to figure out as a proxy. Okay. So, you will have weaker consistency guarantee. The only way you can give the tight consistency guarantee in this case is before every request to the proxy, you actually check with the server if the page has changed. Okay, but clearly that does not make any sense because you put the proxy to reduce interactions with the server. To service a request, if you have to check with the server, you may as well send the request to the server. Why do you need the proxy? Okay. But that is the only way you can actually make sure that you never serve stale content. Okay. But you will never use such an approach because overheads are. Okay. So, this requires more sophisticated proxies. There is a higher message overhead than server push. Okay. In server push approach, every update triggers one message to the proxy. It is an invalidate or an update. In this case, okay, there may be many polls between two updates. Okay, many of them are wasteful, but you do not know what is the right poll duration or poll frequency. So, you are just polling based on some policy that you implemented at the proxy. So, it might waste more network resources because you might poll more frequently. Okay, so, there are pros and cons between whether you use push or pull. Is that clear? Any questions? Okay. So, now let us see if we can get the best of both worlds. Okay. So, we are going to look at a hybrid approach, and this approach is called leases. Okay. This is the first time we encountered the concept of a lease. It is nothing specific to web proxies or caching. It is a more general concept. So, I am going to explain what the concept is, then we will see how to use it for web proxy caching. Okay. So, lease is essentially not very different from a lease that you might sign to rent an apartment. Essentially a contract, okay, with the time duration associated with it. Okay. So, the lease is a contract that has a time, and lease specifies for that contract what is the responsibility that in this case the server or the proxy will assume. Okay. So, you can use the lease for any purpose. You can say for the next 10 minutes I would like you to keep sending me invalidates or updates. Okay. So, server says yes, and so now you have an agreement with the server saying for that duration of time the server is agreed to do something for you. Okay. So, that is the concept of a lease, and it is very interesting to use it in the context of caching. Okay. The main reason you want to use it in caching is server push by definition, okay, does not tell you the approach does not tell you for how long the server has to keep sending notifications to the proxy. Okay. The default duration is assumed to be infinite. Right. Once the proxy has cached a page, the server has to keep sending in notification for life. That does not make sense because very old web pages may not be accessed by any user anymore. Why keep getting notifications for them? Right. But there is no nothing in the server push approach that says stop sending notifications after this point in time. There is no such thing. Okay. Leases give us a way to essentially do that. Okay. You can essentially implement a server push approach with the lease saying, I am going to send you updates or notifications for the next so much duration, which is basically the lease duration. Okay. And for that duration, you are guaranteed after that the server will just stop unless the proxy might request a renewal of a lease or things of that sort. Okay. So that's how we are going to implement this, but we'll get into the details. Yes. Question.
You can essentially have a case where lease seems to be up from the proxy's point of view, but the server isn't up to the proxy for the Screencast, but the server has.
So we'll not worry about time synchronization if that's what you are getting at. Let's not worry about that yet. Let's just focus on what the lease is. But if clocks are not synchronized, lease won't make any sense. But yes, we'll get to that. Okay, so here is the flow. Client will send an HTTP request, which I'm just specifying as a read to the proxy. Okay, first time the proxy gets this request, it's a cache miss. It does not have the web page. It has to go to the server to get a web page. So it's going to send a get, HTTP get with a lease request saying, I need this web page and give me a lease on it. Okay. The server is going to send back a reply with the web page and is going to grant you a lease, okay, with a duration. So there's a time associated with the lease. And what that says is for next so much time, the server guarantees that if the web page is updated, it will send a notification or an update to the proxy. So the proxy knows that until the lease is current, okay, you will essentially, whatever you have in your cache is going to be up to date because the server will tell you if it is not. So you can now serve content from the cache without having to worry about is the item consistent with the server and things of that sort. Okay? So while the lease is current, you are going to keep sending, the server will send invalidates or updates. Once the lease expires, the server can delete that from its state. Okay, so the state no longer has to be kept for infinite duration, but server only agreed to send you updates for the duration of the lease. So you can just expire the lease and stop sending updates. Okay. Now it's the job of the proxy to say once the lease expires, should it renew the lease or not? Should it ask for a new lease or not? Okay. If it sees that the web page continues to be popular, it's getting requests for this web page, so you could say the lease expired, let me get a new lease because I'm still getting requests for it. On the other hand, if the object has become cold, which means that there are no longer frequent requests for the object, you can let the lease expire. And then you can actually, if you want, even invalidate the object from your cache saying lease expired, object, nobody is reading this web page, I'm going to delete it. So next time if there is a request, this whole process will repeat. Okay? Is that clear? So that's essentially how you are going to implement a lease-based cache consistency. Now, if you think about this, this is actually a hybrid between server push and client pull. Okay, you will see that there's clearly a server push component here because when the lease is current, the server is sending you invalidates or updates. Okay? But there's also a proxy-based pull component because it's the job of the proxy to request a lease and also to figure out if you have to renew the lease. Okay, so the proxy cannot be dumb. It has to track what is the popularity of the object. Does it make sense to cache it further? Should I get a new lease on it? All of this has to be decided by the proxy. Okay? Now, depending on the duration you set to the lease, you can make this approach look like a pure pull-based or a pure push-based approach. In particular, if the lease duration is set to infinity, okay, this basically degenerates to server push. Because you get the lease is valid forever, the server has to keep sending you notification for it. That's what the server push approach did. Okay? If the duration is set to 0, okay, the lease comes and expires immediately, then you are back to a pull-based approach where the proxy has to figure out either poll and get a new lease or do something like that. Right? So it's essentially going to give you, for 0 duration, this looks like polling. For infinite lease duration, it looks like push. So anything in between is essentially going to be something intermediate between the two extremes. Okay, now it's up to the server to decide what lease to give for each object, because there is no good lease duration. Again, just as you have to decide the poll duration based on things like popularity, you can do the same thing for the lease duration. Okay, you can say, I set the lease duration based on any metric. It could be age of the object. How long has it been since the object was written to? The object is being updated frequently, maybe I should give longer leases. Okay? Or it is based on how frequently leases are getting renewed is an indicator of how popular the web pages are at the proxy. Okay? So renewal frequency tells you something about the popularity. So if the web page is popular, maybe you should ensure stronger consistency, give longer leases so you can keep sending updates. You can even change the lease duration based on server load. If the load is high, you can give shorter leases and throw away your extra state and reduce the number of notifications you have to send and so on. Okay? There could be many metrics that tell you how to decide the lease duration. Is this clear? Any questions? Yes, please. So first of those policies is saying age based. Age is essentially referring to the age of the web page is the time since it was last updated. So the age is 5 minutes, that says it was updated 5 minutes ago or 10 minutes ago and so. So age based essentially says if your document is old, that means it hasn't been updated in a while. It's not seeing a lot of updates. Okay, so you can use that as an indicator to say what the duration of the lease should be. Okay. So now with that background of server push and client pull and caching, let's come back to this concept of cooperative caching. Okay, how can we now have not one but a collection of caches, okay, collaborate on servicing user requests. Okay, so for this I'm going to actually use a small animation to show you how cooperative caching might work. Okay, so here you have a server at the top, set of clients at the bottom. We have 4 caches. Okay, they're actually arranged in a hierarchy in this case. So there are 3 leaf caches, 1 parent cache. Okay, they're just caching web pages like before. Okay, in this case also you'll get requests for web pages. If it's a mess, you got to somehow fetch that object. Fetch that web page, except that in the previous case, if there's only one proxy, every time there is a miss, you go directly to the server. Okay. Here you have the option of asking other caches before you go to the server. Okay, so there are actually open source projects like Squid and Harvest that essentially implement this cooperative caching, but let's see how it might work. Okay, so here is a request for web page A that goes to this cache. Okay, let's say that it is a miss. Okay, so this is going to trigger a request to other caches saying, do you have A? Okay, this is labeled ICP, which stands for Internet Cache Protocol. That's just a message that says, do you actually have object A? Okay. Now, if this is the first time it has been requested anywhere in the system, it will essentially be what's called a global miss, meaning no one has it. So they'll all reply saying, I don't have it. Okay, so you got a response saying, I don't have it. So now what this proxy has to figure out what to do. So in a hierarchical approach, it is simply going to send that to its parent, and this will recursively repeat. So if the parent has other peers, this is only a single tier, but assume there's a multi-tier hierarchy. The parent had other peers, it would send ICP messages to them, look for that object and send it all the way up to the root. When you hit the root and you have a miss, that is when you're going to get it from the server. Okay, so you see that the message went to the server, you got the response, and then you got it back to the client. Okay. So now you have it, and then you're going to send back the response. Yes, question.
Why do we introduce hierarchical proxy caching?
Okay, why do you introduce hierarchical proxy cache? Is that your question?
Yeah.
So this is just a way to do cooperative caching. Okay, we'll see a non-hierarchical approaches in the next slide. Okay, but the initial design of these caches was we'll have a global hierarchy of caches. There will be lots of leaf caches. There will be higher level caches, and they'll all collaborate in this grand way to implement one big cache. Okay. Yes, question.
Wouldn't this lead to communication overhead?
Yes. The question is, wouldn't it lead to communication overhead? So the answer is yes. So if you look at this, the reason I made this animation is you see that to make one HTTP request, how many messages have been exchanged just to fetch one page. Okay. Not only that, the latency to get that page has actually increased significantly, because it may have probably been faster to just go to the server and get it. Here all of these messages, which all have to get responses, have been exchanged before you got the page, and you are just waiting there for your page to load, and all these proxy are exchanging messages. Okay, so that's one downside. Okay, the upside, of course, is if there was a hit somewhere here, okay, on the first level, you could have gotten it from a nearby cache rather than going to the server. So, there are lots of, let's say you put a cache in computer science, you put one in engineering, so you get it from another nearby cache rather than going to a distant server. That is an advantage, but you will see that there are disadvantages. Yes, question.
Why is there not an additional layer when you first talk to your leaf caches before talking to your parent?
Yes.
You always talk to your parent. The parent might not have it and would have to fetch it.
Right.
And
So
you're always causing that overhead, at least on the parent, if it's on one of the leaf caches.
So you could have just queried the leaf. In this case, you will see that when you query, you send ICP messages. When you send it to the parent to service it, you send an HTTP request. You forward the HTTP request. So when you send ICP messages, it doesn't trigger recursive lookups elsewhere. That's just a query. Do you have it? Yes or no? Okay. And if you said yes, you would have probably been asked to get it. But if you send an HTTP request, you do the same thing. You send ICP messages and queries. So there's a distinction in what is happening there. Having said that, still too complicated. Okay. So we should figure out how to simplify this. So what could we do? Yes.
What if the parent had some state of what the leaf caches do and had it in their cache and it directly query the parent? So that if it had it, it would know the 15th parent doesn't have something that could directly query the leaf.
Okay. Good idea. I'll come back to you because there's another hand up. Yes, please.
If you could do something like a core kind of approach of each cache is responsible for certain bits of information. So you look first, if you don't have it, you look at the other places that might have it in your hierarchy.
Yes. So I think we are going to use some combinations of what you said. So what you said was, let's not ask, let's keep that information upfront. We'll just do a table lookup. If you know what is cached everywhere, just look up a table, see who has it. If somebody has it, fetch it, otherwise go to the server. Okay? So that's obviously a good approach, because rather than asking every time, if you knew what was cached everywhere, then you could just do a table lookup saying, let me see what pages are cached where in my system. If somebody has it, I'm going to go get it from there. Okay? And then you could, of course, partition your cache saying all pages starting from A to Z go here. I mean, not A to Z, means everything is called here. A to C go here and D to something go there and so on and so on. Okay? So those are all good ideas. That's essentially what we are going to implement here. Yeah. So you'll see that the hierarchy is gone. It's flat, because we don't need any roots anymore. We just need to keep track of what information is cached where. Okay, so we are essentially going to start doing table lookups. Okay, I think there's an animation here as well. Okay, so here we got a read for object A. Okay, then you essentially are going to look up your table, which is here, which says who has what. In this case, A is actually cached at node X. You have that information with you. Okay, so you are going to then say, I'm going to get that from from X rather. I got it and I gave it. Okay, so now you're done. Instead of sending lots of messages, you essentially did this. Okay. Now you might have another request for B. Okay. You will see that there's no entry for B, which means the global miss. Okay. Nobody has it. So you look at your table, can't find any trace of any client, any cache rather having B. Just go to the server, get it, and then you give it to the client. And then, of course, you are going to keep it in the cache, and you are going to add an entry saying, I have it. You have to also tell everyone else that you have it. Okay? So in this case, your lookups, etc., have been sped up, but you need to make sure that table is up to date. Every time you fetch a new web page, you have to tell all your peers so that they can put them in the table. Every time you delete a web page from your cache, also you have to tell them. Because if you just delete without telling them, you might have stale table information saying node X has A, but A has been deleted from X's cache long time ago. So every time you fetch or delete, you got to update that table. Okay, so you got to keep that table consistent, but it doesn't have to be super consistent, because even if you make mistakes, that's not bad. Okay? That is what is said here. The first thing is that all lookups are local. You don't have to ask everyone, do you have it or not? You can just check your table. Okay? Hit is at most 2 hops, okay? Which essentially says that you can go to your local cache. It can go to another cache if it's there, or go to the server, one of the two, and then that's it. Okay? And if it has it cached, then it's just one hop. Okay? Misses are also at most 2 hops, because what might happen is you might go to a cache. The cache says it is at actually some other node, but that node doesn't have it, then it has to get it from the server. So that's essentially the one extra on the wrong hint, which means my table is out of date. So in the worst case, if I actually have some slightly inconsistent table, I may have one more hop. But in most cases, I'm going to just have these 2 hops. It's a miss, so you go and get it. Okay, is that clear? Okay. So there are a few things to keep in mind. Now, cache hits and misses have different flavors. There's something called a local hit, which means that my cache has it. There's something called a remote hit, which means that I don't have it, but some other remote cache has it. Okay. And then there's something called a local miss, which means I don't have it, but somebody else could have it. And there's something called a global miss, which means no one has it. Okay. So cache hits and miss will come in different flavors depending on whether you have the object, somebody else has the object, no one else has the object. Okay. So you can analyze the latency. It's basically going to be 1 hop if it's local hit, 2 hops if it's a hit or a miss, and if you get it wrong, there's 1 more hop in there. Okay, but still a lot more efficient than whatever we had looked at before. Okay, yes, question.
So one part that's missing from here is how do you learn about the local hookup, right? You need to know once you get one of the nodes to get that information, how do you propagate it to your
Right. So you're asking how do you keep the table consistent? So this table is, every node has to have, in this case, all the entries from all of your local caches, a global direct. Think of it as a directory. So I have a list of every web page that's cached. So let's say my group is, you don't have to do it for the entire system, but you can say these are my local caches that I'm cooperating with. So within your cooperating group, you go, every node has to keep a global table saying this is what everybody else has, and every other node has to do the same thing, and you have to keep that consistent.
Do you need to send messages to update that when someone
Yes.
gets a new thing?
That's exactly right. So the table, so that's what I said. The table has to be kept consistent with the additional messages that are not shown here. Every time you fetch a web page, you have to send a message to all your group proxies saying, add this entry to your table. Every time I invalidate it, you have to send a message. Okay? That's not table consistency overhead. That's not that's happening in the background, but you have to do that. Otherwise, your tables are out of sync and outdated and so on. Yes. Okay, but that's not on the critical path of finding the serving request. So it doesn't actually increase user latency, but it is additional overhead for maintaining cache consistency. Any other questions? Okay, so I have one more picture to show, which is on content delivery or content distribution network. So this notion of web cooperative caching has been implemented on a much larger scale using systems that are called content distribution network. So there are companies that set up this very large number of caches in lots of networks throughout the world. Okay, the biggest one is called Akamai, but there are many others. Okay, so Akamai has maybe tens of thousands, hundreds of thousands of server caches. It is deployed everywhere, and these caches are going to cache all kinds of content, and then you fetch them from the cache instead of going to the origin server. Okay? So this whole notion of web proxy caching is actually big business. There are many companies that their entire service they offer is essentially deploy a lot of caches. They serve all kinds of graphic rich content or videos which are all expensive to deliver from the end server. Okay? So you cache it and then serve it from proxies that are very close to the client, so the client sees good performance. Okay. There are many ways to implement content delivery networks or content distribution networks. That's basically used those interchangeably. Here's a picture from the book that essentially shows how do you do this with a smart DNS. Okay. This picture is not as important as understanding essentially how a CDN works. Okay. So essentially in the CDN, what happens is the DNS is actually a very intelligent component. Whenever you are trying to make a request to a web proxy cache, it's the DNS's job to figure out what is the closest proxy to you. Because we never actually said how do you know which of these n proxies is the nearest local proxy to you. Okay? Your browser doesn't know. Browser doesn't even know where the proxies are, let alone know which one is the nearest one. So what has to happen is when you are trying to look up the web page, somehow you are directed to your local cache that actually has the content. The way this is done is through essentially a special DNS server, which is going to know where all the proxies are deployed in the network. Okay, let's say you deploy proxies in every country or some such thing. Okay. So when a request comes, it actually figures out where the client is based. So you have to do something called geolocating of the client, saying where is this client, where is this IP address actually based. Okay. So if we say, okay, this is actually coming from Massachusetts or Amherst, then you say, where is the closest proxy I have that is close to this client. Okay. And then as response to the DNS request, you send the IP address of that client. Okay. So different clients for the same request will be sent off to different proxies, the one that is closest to them. Okay. That will cause the browser to automatically connect to that proxy because the DNS resolution actually returned to you the IP address of the closest proxy. Okay. And then you can just connect to that proxy and get it back or get it from there. So that is essentially what is shown here. So, so there is essentially a client here. You'll see there's origin server. You get the HTML page, but if there are big images, they're assumed to be put in that CDN server. So then you try to do a DNS lookup for those images, and that essentially ends up at the CDN DNS server, which says where is this client geographically, where is of all the thousands of proxies I have, what's the closest one, and that's essentially that one. And then you get the IP address of that one from the DNS server, which causes you to connect to it. So that's essentially how most of the CDNs work. Okay. Now CDNs don't necessarily implement a lot of cache consistency. They push that burden to the content providers, and you can update the content whenever you want. So they are not going to implement some of the schemes we talked about. Essentially, it has to be done as a push from the origin server. So it's up to whoever is publishing this content to decide when to update the proxy. Okay. So with that, we ran over time a little bit. We'll end it here, and we'll continue next week. Okay. Thank you.